Hey guys, welcome to Pointers, a C++ series. This is part 3 of the series, so if you didn't watch part 2, there'll be a card right now above. Make sure click that, watch that, and then come back here. And if you're completely new and didn't watch part 1, then there'll be a link down below in the description. Go ahead and click that and start at part 1. But if you're all caught up, cool. My name is Ghost, and in this video, we'll be going over the common pitfalls of raw pointers. Let me stop rambling. Let's just get right into it. Okay, so if you've been following along, you know that there is a repository. The link will be in the description below, but in this repository you're going to want to go to part 3, which is this video. So let's go ahead and click this, and we're going to go to our source here, which is where all the CPP files exist. Now this video I'm going to go over 9 common pitfalls. This isn't an exhausted list, of course there are more, but these common pitfalls I feel relate more to beginners, as I feel beginners make these mistakes quite often when learning pointers. Now as I go over some of these pitfalls, they may be somewhat familiar to you because in the last videos I went over some of them already, like memory leak. So yeah, if they seem familiar, that's why. But I'm still gonna go over them again with a little example, so that way it's all in one video. Anyways, let's begin. So we're gonna start with number 1 here, which is the uninitialized pointer. Okay, so the first thing I'm gonna say is that you're gonna see these README comments here, and you can open them up on your own time. I'm not gonna go through them, but they're just there for anyone who downloaded the repository and is browsing through each individual CPP file. Anyway, so let's just go over the pitfall. So uninitialized pointer. And what that means is when we declare a pointer, but we don't initialize it. And I mean, like, don't initialize it to something like this, or don't initialize it to something like, in this case, which we will go over, null pointer, if it won't point to an actual piece of memory. So when you just declare it like this without initializing it, what happens is it'll be set to some garbage memory address. It won't be null or 0. Now immediately you can see that's probably an issue, because if it's pointing to some random piece of memory on your computer and then you try to use that, you're going to have some undefined behavior happening. So right below the declaration, I do have the correct way, which is just initializing it to null pointer. And what I mean by that, let's say you need a pointer, but you don't know what it's going to point to yet. Well, we already addressed that we can't leave it uninitialized. So what you're going to want to do is use this null pointer. And what this null pointer is that it's a null pointer constant, which represents 0 in essence. Now, why not just set it to 0 like this, or just use null, which we know is a macro which expands to 0? Well, it's safer than null or using 0 in modern C++ because it is typed, meaning that the compiler understands that when you use null pointer like this, it understands that the value you are giving it, which is going to be 0, is not an integer. It belongs to a pointer, which represents memory addresses in value. Now there are cases where that could become an issue if you use a 0, because it will assume that you're referring to an integer. So whenever you have a pointer that will not be pointing to a valid piece of memory, make sure to use null pointer like this. Don't use 0 and don't use null. Now for ha-has, let's say we left it uninitialized and then we try to run this here, which is basically your dereferencing, right? Because we're using this asterisk in front of the pointer. So you're attempting to get the value at this memory address and print it here. What's going to happen is that it's going to lead to undefined behavior. Now, what you're going to see is some weird long number, most likely. I'm going to run it and you'll see exactly what I mean. And there you go. See, you see some weird long number, and it happens to be a negative number. We don't really know what that is, right? So that's that undefined behavior that we're gonna see. Also, really quick to prove that it is a memory address that gets assigned to this uninitialized pointer. It just happens to be some random address. I'm gonna actually print this memory address by removing this dereferencer, and we just change this to just say pointer like that. And let's run this again. And like I said, there it is. It is a memory address. It just happens to be a garbage memory address. And that's why we had that weird long negative number. Okay, so the last thing I want to go over before we move on is these classes up here, because where this is common, where you don't initialize a pointer, is usually in these classes. This is where I see a lot of newbies doing it. So if we open up this class here, it's just a class. It's empty. It's just a vet. But if you open up this class here, the animal, we use this class here, the vet, as a pointer, but notice it's uninitialized, right? And we already know that leaving it uninitialized will set it to some garbage memory address, which could lead to problems down the road. So the recommended way is to just set it to null pointer. However, you need to know that this is a C++ 11 or later. So if you are using anything older than C++ 11, this won't work. You can't initialize any members of a class like this. So the other way of handling this will be to set it down here in the constructor, which in this case, I'm using the member initialization list. Now, let's say you're using C++ 11 or later. Why not do it this way all the time? Well, the problem is that if you have multiple constructors, you must remember to initialize each one. And that's what you see down here. This constructor accepts an integer age, which now you must remember to include this in this constructor. So the easiest approach and recommended way, if you're using C++ or later, is to do it this way where you just initialize it directly in the class like this. Believe me, you don't know how many times I made that mistake when I was a newbie. Anyways, let's move on to common pitfall number 2, which is attempting to dereference a null pointer. What I mean by that is by initializing or setting a pointer to null pointer and then trying to dereference it later on. That is going to create undefined behavior. Okay, so as you see here, we have our pointer, which we initialize to null pointer. So down here, when we are attempting to dereference this pointer, when we're printing, it's going to cause an undefined behavior. Now, I'm not entirely sure if it's dependent on the compiler or architecture, but it may crash the program. But in my case, which I'm on Windows, it doesn't crash my program, but it does do some weird stuff, which you'll see in a little bit when I run it. But before I do that, let me explain the correct way to approach this. So if you look at this if statement right here, we are checking this pointer to see if it is pointing to a valid memory address. Now, we're able to do this because it implicitly converts it to a Boolean. The reason why it does this, because remember, null pointer is essentially 0. And what does that mean as far as Boolean goes? It means false. Now, if it isn't 0, if it's a 1 or any value higher, which a memory address will be some value higher than 0, it just means that it's true. So by making this if statement like this, we just implicitly convert it to a Boolean. So since this pointer is set to null, we know that this isn't going to run because also remember, a memory address is an integer and any valid memory address is never a 0 because that would just be null pointer. So since essentially it's a 1 or higher, then this is true. But we know that it's null pointer, so we know it's not going to be true. So it's just going to be the else statement. Now, this check right here isn't a surefire way of dealing with pointers. It isn't checking if it's a valid memory address or if there is actual memory at that supposed address. Now, the reason why I say it's not a surefire check when dealing with pointers is because if you look here, if we remove this null pointer, so now it's just some random garbage memory address, this right here will technically be true. But it's just some random garbage memory address, right? So if we try to dereference, we're gonna get that same issue that we got in the last pitfall. Okay, so let's run this. But before I run it, let me explain what you're going to see. So since we're leaving this line inside of here and not commenting it out, what's going to happen is we're going to attempt to dereference this pointer, which we know is null pointer. So what we're gonna see in my case, I'm on Windows, what we're going to see is we're going to see this print here, and then you're obviously not going to see nothing here because there is no valid memory there to see anything. But then technically you should have seen this next, which is this pointer is null pointer, because remember, we are checking this here, but that's not what you're going to see. The reason why is because of the undefined behavior that is going to happen because we are attempting to dereference a pointer that is currently set to 0. Okay, so it's as I said it. So we see this value at pointer, which remember is this right here. We don't see anything after that because we're not going to see anything. It is attempting to dereference a pointer that is set to 0. But notice we're not seeing that other line. And what I mean is this line right here. It did not print. It should have, but it didn't. That is the undefined behavior that will continue to arise because of this up here. Also notice it didn't crash the program. It's just doing weird stuff. Undefined behavior. Now, if I remove this, which is the point to this pitfall, what we're going to see now is this line here. And it's exactly like I said, pointer is set to null pointer. Okay, so for this one here, we see a function here, which this is going to be the wrong solution, and this is going to be the right solution down here. We'll go over that in a minute. But what this function does in this case is it is creating a integer, but remember, it is on the stack because we're not using the new keyword. So this belongs to this temporary frame right here, which is the function, meaning we won't have access to this in this main stack right here. Notice the return type is integer asterisk, which is for the memory address that we're attempting to return. And you see that right here. We take our X variable and we use this ampersand, which is address of. So we're attempting to get this memory address and return it to the caller, which is going to be down here. Now this will create an error. Now you should already know the reason why. This memory exists on this stack right here, this temporary stack. So attempting to return the memory address so we can try to gain access to this piece of memory here is just not going to work at all, because this gets popped from this temporary stack once we are leaving it at this point here. So really, what is it going to return? It's just going to cause an error. So this is the caller, and we're going to attempt to assign that memory address here to this pointer here, and then we're going to print out that address and then print out the value at that address. Okay, so this is interesting. The compiling didn't cause an error, but it did give us a warning, and that warning is the address of a local variable X returned. So what it's stating is that you can't do that. It is a local variable. It belongs to that certain stack, this temporary stack here for the get pointer function. We can't return it. It's impossible because it gets popped from this temporary stack, and the whole temporary stack goes away after it returns back to caller. And at this point here, it's just letting you know where it was declared at, which is right here. But it's just a warning. It technically did compile and it did run, and we see it down here. So the address that we got is 0. And I believe the reason why it's 0 is because, remember, this address was tossed out. It didn't exist no more. So I think what the compiler did was just set it to 0, to essentially null pointer, and that's what we got. So then at this point, when we're trying to access the memory, we're trying to dereference it right here. We're essentially doing the same thing we just did in the other pitfall, which is just going to create some undefined behavior, which is what we see again. And that's why that blue line is just up here, because everything that we're doing after is just causing some sort of issue, because we're attempting to dereference this pointer, which is essentially set to null pointer. So in essence, all we really did was just do this. That's pretty much all we did when we called this function here. So the solution to this type of function, if you want to create something like this, would be down here. So with this function here, we're still returning a pointer, but in this case, we're allocating to the heap, and that's what we do right here using the new operator. And we know that the new operator is going to return a memory address, so that's what we just pass right here to the return keyword. So now when the caller calls this function, it is going to get a real memory address to some memory that exists on the heap, which we know the heap is a long term. So it will get that memory address assigned to here. So when we run this here, which is going to be the address of this pointer, and then run this line here, which is going to dereference, it should give us a valid memory address and then 10. Let's run it. And there we have it, a valid memory address and 10. Okay, so moving on to the next pitfall. Now for this one, I believe I already went over it in part 1 and I think in part 2, but that's memory leak. So yeah, this should look very similar if you recall part 1 and part 2 where I did cover this, but I'm just gonna cover it again really quickly. So we have this function up here, which is going to allocate some memory, and we call it down here in our main function. But looking up here at our function, the first thing that we do here is allocate new memory to the heap, but then we don't do anything else. I mean, we print this here, but it doesn't matter. Now, if you can recall, that is an issue because we lose access to that memory, hence memory leak, because the pointer exists in that temporary stack of that function. When we return back to caller, the caller won't have any way to access that memory because that pointer existed in that temporary stack. Now, if we do something similar to the last pitfall where we actually return that memory address, then cool, that would work. But we're not doing that here. The return type is void, as you see right here. So we're not returning this memory address. We're just allocating this memory on the heap, which we know is long term, and then we don't do anything with this memory address, which is assigned to this pointer afterwards. Now for this case specifically, the only best approach is to do this here, the delete pointer. So I won't go over the reasons why this is an issue because I already went over that in the last video. So if you did not see part 1 or part 2, make sure to go and check them out and then come back here. But remember, I also do have this readme here, which does go over what a memory leak is, why it's bad, and then the the best practices. Anyways, let's continue on. Okay, so the next pitfall is dangling pointer. Now, I think I went over this as well in the last videos, but if I didn't, let's just go over it real quick. All right, so here we are. So the first thing that we're gonna do here is allocate some memory on a heap, which type integer, value 42, set the memory address, which is returned from the new keyword, to this pointer here. And then we're gonna actually free that memory using the delete operator. But the problem here is that we are attempting to dereference this pointer, which was pointing to some valid memory, but was then freed. This is what you call a dangling pointer, because it is still pointing to the memory address where this once was. But the problem is, since it was freed, now technically what I should say, I don't want to confuse you, but it isn't deleted immediately, like meaning the memory isn't freed right away. It's just primed for being deleted. But attempting to dereference from that memory address will cause an issue because it is memory that is prime for getting freed. I don't want to go too deep into the specifics of that, but yeah, I just wanted to mention that real quick. Either way, it is still considered a dangling pointer because it is pointing to a memory address which no longer has that memory. So whenever you are freeing memory like this, you want to set that pointer to null pointer so it isn't dangling anymore. It is just set to 0 essentially. Okay, so there it is. Some long number, which that is not 42. So yeah, obviously that's wrong. It's just undefined behavior. Okay, so for this next pitfall, it is attempting to free the memory twice. And what I mean by that is using the delete operator twice on a pointer back to back. Or at least in this example, it is literally going to be back to back. This can happen in other ways though in your program where it is somewhat back to back, but just spread out in your code. But it is an issue and it should be avoided. Let's get into it. Okay, so what we see here is allocating a heap and then getting that memory address, setting it to this pointer. And here we are dereferencing, which should work because there's no issue, right? We didn't free the memory and it is pointing to some valid memory. So we should see 42 here. Next, we are freeing the memory and that's fine. Nothing wrong with that. We're just getting rid of the memory. We didn't handle the dangling pointer issue, which remember is just setting it like this, null pointer. But that's not the point for this example. The point is that we are attempting to delete. Again, that's going to cause undefined behavior. I feel like undefined behavior is literally going to show up in your dreams tonight. Sorry about that, but all these things are just undefined behavior. Okay, so let's just run it and see what's going to happen. Okay, so we do see value 42, and then we don't see anything else. No, that's because we're not really doing anything else down here. So once we call this delete pointer again, I mean, there's nothing happening. The program terminates, so we don't really know if something happened. So what we could do is we're just going to print something random here. A simple little hello world. Okay, so yeah, there is something happening because we do see that value 42, but remember that happens before the issue. And then we attempted to print again, hello world. We should have saw that and we didn't, obviously. That's that undefined behavior that we're talking about. Everything that comes after this would cause issues. Now, I'm not entirely sure, but in some architectures, it may just crash the whole program. But obviously, the simple fix in this case is to not attempt to free the memory twice. And remember to deal with your dangling pointers by setting your pointer to null pointer like this. So we're going to remove that. We're going to take our pointer here. We're going to set it to null pointer because we don't want dangling pointers. Let's run this. And there we go. Value 42. Hello world. Everything is working great. Okay, so this next pitfall is a big no-no. And I do believe that newbies do make this mistake when they first learn about the delete keyword. And that is attempting to free memory that belongs to the stack. So if you look here, we allocate memory on the stack, which is our X variable, integer set to 10. And then we create a pointer, which also will be on the stack, get the memory address of this X variable, which remember is a stack memory address. It isn't heap. But then we make the mistake right here to free this memory. Now, some of you may be thinking, duh, I will never do that. Delete is reserved for heap allocated memory. But you'll be surprised. Some newbies get it confused because they don't know the difference between stack and heap. They don't even sometimes know what it is. They may have just learned a little bit about the delete operator and they use it on something like this, a stack allocated piece of memory. So yeah, don't do this. The simple fix is just to comment it out. Don't do it. I'm not even gonna bother compiling and running this because what do we know about this? It's going to be undefined behavior and it's going to also show up in your dreams. Anyways, moving on. Okay, so we're down to the last two. almost done. Which reminds me, if you haven't liked this video yet, please consider doing so. If you haven't subscribed, definitely consider doing so and hit that bell notification. If you have any questions, comments, or concerns, leave it in the comments below and I will answer back. But let's continue on to the next pitfall. And that is number 8 right here, which is mismatched delete. Now, this is one of those pitfalls that I did go over, I believe, in part 2. So if you can recall, we have 2 delete operators. We have this delete operator, which is by itself, which is for single objects. And then you have this delete operator using the brackets, which is for something like arrays, which is not single objects. So you should already see the issue here. We're allocating new memory in a heap, which happens to be an array, and we set the size to 5. So of course we get the memory address from the new operator and we assign it to this variable here. And then next we are attempting to free that memory. But the problem is we're using this single delete operator and not this correct operator here, which uses these brackets. Well, that's going to create undefined behavior once again. But in actuality, what it's going to do is attempt to remove the first element of this array. Actually, what I should do is initialize the array with some data. So let me just do that. Okay, just to visually explain what's going to happen. Let's say we set the first element to 20 like this. So what's going to happen when we use this delete operator with our variable here? It's going to attempt to free this memory here. If you recall from the last video, when you're dealing with arrays that are allocated to the heap, the memory address that is returned is from the first element. So this pointer here is pointing to the first element of the array. So for extra clarity, I just set all the other elements. So this pointer here refers to the memory address of the first element. So once again, once we attempt to use this delete operator like this and not the correct way using the brackets, it's going to attempt to free the memory at the first element here, and it won't attempt to free the memory of the entire array. That is because it's treating it like a single object, since we're just using the delete operator and not the delete operator with the brackets. So I'm actually going to attempt to print the first element and then the second element just to see what happens. Yeah, weird stuff is happening. So that first element, which should be 20 as we see here, is some weird random number, negative number. And yeah, so that's undefined behavior. And then the second one, which should technically be 30, is 598. So yeah, so like I said, it's undefined behavior. Okay, really, I'm sorry if undefined behavior ends up being dreams tonight. Don't come back in the comment section and attack me. But I'm probably gonna say undefined behavior a few more times before this video ends. Okay, so let's get this correct. So we want to free the entire array. So it's pretty easy. All you're gonna do is just put brackets at the end of this delete here. Okay, so for this last one, I'm pretty sure I went over in part 2, but that is pointer arithmetic. You have to be very, very careful to not go out of bounds. Okay, so the first thing that you see here is that we create a constant. That's just going to be for the size of our array. And that's what you see here. This is allocated to the stack. Now, the next thing we do here is declare a pointer, and we initialize that pointer to this variable here. Now, if you could recall from the last videos, you would not use this ampersand like this because remember, array is already pointing to the memory address of this element here. All right, next, this is the problem here. Now, I'm not going to touch on pointer arithmetic. I did go over that in the last video, so I'm not going to waste time explaining it. But as you see here, we are attempting to move down this array by 5. But as you see, we only have 3 elements. So we are going out of bounds. This pointer will eventually point to some other memory address that doesn't belong to this array. Thus create what? The undefined behavior. Sorry guys. Anyways, to correct this, you would just do something like this, where you just take the size, and that's why I have this variable up here, this constant. So yeah, you take the size here and you subtract 1 because remember arrays start at 0 and not 1. So you need to go to 2, which will represent this last element here. And yeah, so if you do something like that, then you are within bounds and it will work. Now for the next example here is another case which will be familiar when you're using loops. This line here just sets the pointer back to the first element. So anyways, looking at our loop, we have this integer which is set to 0. And then our condition goes up to 5, which is sort of what we're doing here, right? But in this case, how we're doing it is that we're incrementing by 1 per iteration. So for the first 3, it will work and it will produce the values starting at 10, 20, 30. But then when we get to that next iteration, what is going to happen is we're going to be out of bounds because it's going to go past the array size. So essentially, we're going to have those 2 words there. I won't say it. So the solution for this is the same thing that we did up here, the size -1. We just replaced the 5 with that down here and we should be fine. So before I run it, I'm actually going to comment this out, and we're just going to run the correct versions to make sure that it does work. So I'm actually going to add a print up here so that way we know what this is. It should be 30. And there we have it. So the first print here, which should be this right here, which remember, we took our pointer and we used this operator plus equals, use the size -1, so make sure that we get to that last element, which is 30. That's what we see here. And then by running this line before we run the loop, all we did was take that pointer and set it back to the first element, which is 10. And that's why when we run this loop here and we begin printing starting at 0, the first element, we see value 10, 20, 30. And that's it, because we reached the end because of this condition right here. And that's it. That's all I have for you. That is the common pitfalls when dealing with raw pointers. Now remember, this isn't an exhausted list. This is just the most common. Anyways, I hope this clarified everything with raw pointers. I know there's more to it. You know, it's hard to make tutorials and talk about everything, but I hope from the last video, which is part 2, and this one, that you have now a better understanding of raw pointers and a general understanding of pointers. But in the next video, which will be the last video, I will go over smart pointers. Now I was going to break that video in 2, where I would go over the concepts of smart pointers and resource acquisition is initialization, and then in the second video go over the implementations of the smart pointers. But I'm just trying to conclude this series so that way I can move on to other videos. But don't worry if you're worried about the runtime of this last video. I believe I can get it to a manageable amount, hopefully under 1 hour. Wow, hold on. Okay, so I had to shut that one. That was nuts with all the freaking sun rays. And anyways, let me compose myself real quick. Anyway, so that video should come out next week, but if you're viewing this in the future, then it should already be out. But let me not take up any more of your time. If you enjoyed this video, please hit the like button, comment below if you have any questions or concerns. If you haven't subscribed yet, please consider subscribing, and the notification bell is optional, but would be nice if you hit it. Besides all that, I am Ghost, and I'll see you in the next video. Oh yeah, really quickly, undefined behavior. Sorry.